Hello students. Now in the previous video we discussed some of the problems on partial fraction expansion which related to inverse transform. We took the examples by using a long division method and how the partial fraction can be applied when the numerator power is equal to n or if it is greater than n. Okay. In this video, we'll go to the next method of finding the inverse transform, that is a power series expansion method. Now, in this power series expansion, from the definition of inverse transform, we have this expression x of z is equal to summation n varying from minus infinity to plus infinity x of n z to the power of minus n. Okay. Now let's call this as equation 1. Now if I expand this summation, if I elaborate, that means if I keep on giving values from minus infinity to plus infinity, so how this will look? Let's see. So I will apply the value. I'll start with x of minus infinity z to the power of infinity plus, so I'll go all the way and I'll bring somewhere here x of minus 2 z to the power of 2 plus x of minus 1 z to the power of 1, and continuing this plus x of 0 z to the power of 0 plus x of 1 z to the power of minus 1 plus x of 2 z to the power of minus 2, and it will go all the way to x of infinity z to the power of minus infinity. So let's give this expression a name 2. Now based on this, if you look at this expression, so the name says power series expansion. That means it is mainly related to the power of z, and this expansion is as a series operation. Now what we have as equation 2, so that is the power series expression. Okay, this you have to remember, because if you look at this, whatever z having, whether if it is positive or negative, the coefficients of z will give you the value of the sample at that instant of time. That means if you take this z inverse, the coefficient of z inverse is x of 1. So whatever value you have at x of 1, that coefficient for z inverse, so that will be the value of x of 1 here. The quotient of z to the power of minus 2 is x of 2. Now whatever value you have as the coefficient of z to the power of minus 2, so that will be the value of x of 2. Same applies here. The z to the power of 2 is there, and its coefficient will be the value of x of minus 2, and z to the power of 1 is there, and the quotient of that will be the value for x of minus 1. Okay, so whenever you have this term inverse, you have to find inverse Z transform, you will be given the Z transform of the sequence. Now in that Z transform, you have to perform a long division method. So the long division method, you will get the quotient, okay, and it won't be like 2 or 3 steps you will get the answer. It is a process because it is varying from minus infinity to plus infinity depending on the ROC of the Z transform. So you have to identify whether it is a positive time sequence or it is a negative time sequence. Okay, so if it is a positive time sequence, you have your quotient should have the powers which are, you have to consider this one because this is positive time sequence. If you observe this, the positive time sequence have the inverse power for z, z power minus 1, z power minus 2, and z power 0 as well, which is nothing but 1 here. And if you take the negative time sequence, it's from minus infinity to till here, if you observe, the powers of z are positive. So that means if the given Z transform is a positive time sequence, then you have to arrange the divisor and the dividend in the long division method, so that you should get the quotient with having only negative powers if it is a positive time sequence. If it is a negative time sequence, so you have to arrange both the dividend and the divisor in such a way that your quotient should have only positive powers for Z. Now we will go for certain steps, and we can't calculate for all the way to infinity. So we will go to find some 4 or 5 steps, and we'll stop there because the process will keep on going. And when you do that, your quotient will be compared with the power series expression, which is this one, this expression. So this expression is the power series expression. So now we are going to compare that with this one, and based on the coefficients you will get the respective values. That is, the quotient of z square will give you x of -2, quotients of z power 1 will give you the value of x of -1. That you have to uh, figure it out while comparing with the value of power series expression. And after that, whatever the quotients you will get, so that will be the value at that instant of time for x of n. So this is the process for power series expansion. Okay, I'll just write it down here. After writing this, by comparing the given transform with equation 2, we can obtain the corresponding discrete time sequence x of n. Okay, so that means the coefficients of z to the power of -n is the sequence values of x of n. So this you have to remember. Let's take an example here. Find the inverse Z transform using power series expansion method. So note that if it is asked as partial fraction expansion, you have to use that method only. If it is mentioned as power series expansion, then you have to use the power series expansion only. Now this expression of power series you have to remember. So given x of z is equal to 1 divided by 1 minus, so they are given as 1.5 z inverse. If it is given in fraction, better to convert into uh, the decimal point, or if it, better convert the fraction into this decimals, it will be easier for you to perform long division. Okay, with ROC z greater than 1. Okay. So first and the most important thing is you have to look out for the ROC here. So ROC Z is greater than 1. Therefore, it is outside the circle of radius 1. Hence, x of n is a right-sided sequence or positive time sequence. So this you have to figure out first, positive time sequence or negative time sequence. Now since it is positive time sequence, if you look at the expression, all positive time sequence will have the power of z as negative. So that means you have to arrange your divisor and the dividend into in the form that you should get the quotient with the negative powers only. Okay. So let's see. So after this, mention a point here. Therefore, convert x of z into power series having only negative powers of z. So just in the case if you forget this, I'm writing it down for you so that you can remember that. It will take much time. So since 1 is the numerator, we can't change this one. But if you look, I will write the denominator as it is 1 minus 1.5 z inverse plus 0.5 z inverse. So don't get confused here. Why I'm writing this denominator as it is? In the previous video, while we were performing long division method, both the denominator and the numerator were arranged by default as a highest power to lowest power in that case. Okay. But here in power series expansion, depending on the ROC, whether it is positive or negative time sequence, you have to select the proper way of arrangement for your divisor and the dividend. That is important. Now if you go with the highest power to lowest power, you won't get negative powers, you will get the positive powers. Now if you are getting positive powers and you have a positive time sequence, then it is completely wrong, because positive time sequence will have negative powers as I have shown in the power series expression. So that is why you have to be careful at this point. Okay. So if you are getting positive powers and your ROC says that it is a positive time sequence, then you are making a mistake. Immediately you can stop there and go back to from the beginning and arrange the denominator in such a way that you should get negative powers of z in the quotient. So that is that you have to be careful about. Okay. Now the first thing is to eliminate the first term in long division method. So 1 and 1 is there, so I'll just multiply with 1. 1 into 1 is 1 minus 1.5 z inverse plus 0.5 z inverse. So sign will change, so these two get cancelled here. So this become 1.5 z inverse minus 0.5 z inverse. Next, I have to eliminate 1.5 z inverse. Since the first term is 1, I have to just multiply with 1.5 Z inverse. So 1.5 Z inverse minus 1.5 into 1.5 will get 2.25 Z inverse plus 1.5 into 0.5, 0.75 Z to the power of, if you observe this, we have Z inverse and Z inverse. So this power will become 2 and this power will be 3 here. Now if you go for this is minus, this become plus, and again this is minus. So these two get cancelled. So 2.25 Z power minus 2 is there, and here I think this power is also minus 2. So you get minus 2 here as well. Okay. Now my plus 2.25 and minus 0.5. So that will give you 1.75 Z to the power of minus 2. And this one is minus 0.75 Z power minus 3. Now we have to eliminate 1.75 Z power minus 2. So that's why I'll just multiply with 1.75 Z power minus 2. So that gives 1 into 1.75 Z power minus 2 as 1.75 Z power minus 2 minus, now 1.5 Z inverse into 1.75 Z power minus 2 is there. Now if you multiply that, you will get minus 2.625 Z power minus 3, because we have minus 1 and minus 2, plus 0.5 into 1.75, that will give you 0.875 Z power minus 2 and Z power minus 2, you will get Z power minus 4 here. So first term will get cancelled, and here the sign is plus and here the sign is minus. So 2.625 minus 0.75, so will give you 1.875 Z power minus 3 minus 0.875 Z power minus 4. So now I have to eliminate 1.875 Z power minus 3. So I will multiply with 1.875 Z to the power of minus 3 here. So again multiplying that, 1 into 1.875 Z power minus 3 will get the same, minus 1.5 into 1.875. So that should give you 2.8125 Z to the power of minus 4, because we have Z inverse and Z to the power of minus 3 there, plus 0.5 Z power minus 2 into 1.875 will give you 0.9375 Z to the power of minus 5. So again, if you go for this, so these two get cancelled. This is plus and this is minus. 2.8125 minus 0.875 will give you 1.9375 Z to the power of minus 4 minus 0.9375 Z to the power of minus 5. And again I have to eliminate this term. Now we have 1, 2, 3, 4 steps is done. Let's go for one more step. So I have to eliminate 1.9375 Z to the power of minus 4 here. So 1.9375 Z to the power of minus 4 plus, not plus, I think minus 1.5 into 1.9375 is there. So that will give you 2.906 z power minus 5 and 0.5 into 1.93. You should get zero point 0.5 into some somewhere between plus zero point 0.9 some value z to the power of minus 6 here. So it will keep on going, and again the same repeated process you have to continue. You put a dot here because we can't keep going till infinity, and here you get just put plus and show some dotted lines that indicates the process will go on. So it will go all the way till infinity. We can't calculate there. So go for some 5 values minimum. So 1, 2, 3, 4. So we have done 5 steps here, and the remaining will be the same continuous process. Now what you got as the quotient here, so that will be our x of z here. So x of z, so this is the transform. X of z is equal to 1 plus 1.5 z inverse plus 1.75 z power minus 2 plus 1.875 z power minus 3 plus 1.9375 z power minus 4 plus so on. Now this is the power series expression. Now comparing this, comparing x of z with this expression with power series equation, or sorry, expression. So I'll just take you back to the power series expression here. Now z power 0, that will be x of 0. Quotient of z inverse is x of 1, z power minus 2 is x of 2, z power minus 3 is x of 3, z power minus 4 is x of 4. So this process will continue. So based on that, so we can write, so x of n is 0 for n less than 0 because it is a positive time sequence depending on the ROC. Now x of 0, comparing this, we get x of 0. Now in place of x of 0 we have 1 here. Now the quotient of z inverse is 1.5, that is x of 1 is equal to 1.5, or you can just write it side by side. X of 1 is equal to 1.5. Now coefficient of z power minus 2 is 1.75. The quotient of z power minus 3 is x of 3, which is 1.875, and coefficient of z power 4 is x of 4, which is 1.9375. So we can write our x of n finally as 1, 1.5, 1.75, 1.875, 1.9375, and so on, where this is the origin. Okay. Now this x is equal to x of 0. So this might appear in the negative time sequence because we have to know where the origin is. So that's why it will be present both in the positive time sequence and negative time sequence as well. Okay. So that is the where if it is negative time sequence, we have to show from minus infinity to the origin. So that's why. Now for the same problem, same x of z, what if it is a negative time sequence? So for the same problem, if it is a negative time sequence, how things will differ? So let's see that. In this one, I'll take the example in this way. X of z is equal to, so I'm not going to mention that find the inverse z transform using power series expansion method, because I'm taking the same problem with the ROC changed. With ROC Z less than 0.5. Now the ROC is inside the circle of radius 0.5. So that means ROC is inside the circle of radius 0.5. So therefore x of n is a negative time sequence. Okay. So therefore what we have to do? So we have to convert x of z into power series having only positive powers of z. So the powers of z should be positive. Now how we are going to convert? By long division method. Okay. So let's take this part. Since the numerator is 1, so I'm just leaving that as it is. Now since the power of z should be positive, because it's a negative time sequence, you can see this expression. I'm just taking back here. So powers of z are negative here and here. Okay, so that is the reason. So that's why I will be arranging as in this way: 0.5 z power minus 2 minus 1.5 z inverse plus 1. Now as usual in the power series, the first term should be eliminated. Now to get 1, we have first term as 0.5 z to the power of minus 2. So that means we have to multiply by z square, so that becomes z power 0. Now we have 0.5 as coefficient. Now if you multiply with 2, 2 into 0.5, you will give it as 1 here. So 1 minus 1.5 into 2 is 3. Z power minus 1 and z square, you will get z plus 2z square. So these two get cancelled. So this changes, sign will changes, that becomes 3z minus 2z square. Now the first term is 3z, we have to eliminate that. We have z power minus 2. So to get z, I have to go with higher power than that, that is z power 3. Z cube and z power minus 2, you will get z there. And we have 3, we are 0.5 is there. That means we have to multiply this with the 6. 6 into 0.5 will give you 3 here. So 6z cube multiplied by 0.5 z power minus 2 will give you 3z minus 6 into 1.5 is 9, and z cube, z inverse, you will get z square here plus z cube. Now again these two get cancelled. This is plus and this will become minus. So 9z square minus 2z square, you will get 7z square minus z cube. Now to eliminate 7z square, I have to choose higher power z4, and to get 7 I have to multiply by 14. So 14 into 0.5, you will get 7 z square minus 1.5 into 14. you should get, I think it is 6z cube. I just written z cube here. 6z cube. Same goes here as well. 6z cube, because 6z cube into 1. 21 into 1 point, sorry, 21 z to the power of 3, because 4 is there, z inverse is there, plus 14 z to the power of 4. Now this, then this to get cancelled. 21 minus 6 is 15, minus s z cube, minus 14 z to the power of 4. So we have done 3 steps. We can go for another 2. The highest power z5, because I want z3, z power minus 2 is there. To get 15, I have to multiply this with 30. So 30 into 0.5 gives you 15. Z power 5 and z power minus 2 will give you z cube, minus 30 into 1.5 is 45, z to the power of 4, plus 30 z to the power of 5. So this get cancelled. This is plus, this is minus. 45 minus 14 is 31, z4 minus 30, z5. And we got one more step here, plus the power is z4. I should go with z to the power of 6. 31 is there. So I have to multiply this with 62. 62 into 0.5 will give you 31. 31 z to the power of 4, minus 1.5 into 62. I think we should get 93 into z to the power of 5, plus 62 z to the power of 6. So this get cancelled here. This is plus and this is minus. We'll get 63 z to the power of 5 minus 62 z to the power of 6. And this will keep on going. Now you can stop here. Since you have done 1, 2, 3, 4, 5 steps, you can stop this and you can just say the dotted lines. Now coming to the expression, you have to arrange this in a form. The quotient x of z is equal to, again you have to got 2 to z square plus 6z cube plus 14 z to the power of 4 plus 30 z to the power of 5 plus 62 z to the power of 6, and so on. Okay. Now comparing x of z with power series expression. So we have, so first thing is x of n is 0 for n greater than 0, because the positive term sequence is not available. Now coming to x of 0, we have to check the values. If you see, we don't have anything z to the power of 0, so that's why x of 0 is 0. Coming to x of 1, we don't have z to the power of 1 term, so x of 1 is also 0. Coming to x of, not x of 1, I think it's x of minus 1. X of minus 1 is 0. Now coming to x of minus 2, the coefficient of z square is x of minus 2. I will take you back to the power series here. So quotient of Z2 is minus 2, Z cube is minus 3, Z4 is minus 4, and so on. Now the same thing applies here. So Z square, the quotient is 2 here, and Z cube we have, so that means x of minus 3 is 6 and x of minus 4 is 14, x of minus 5 is 30, and x of minus 6 is 62. Now we got the values for x of n. Now if you arrange this, so remember while arranging this, if you see the power series, so it is starting from minus infinity and it will comes all the way to 0, minus 2, minus 1 and 0. So you have to arrange in the same way, it will be better. So I'll start with so minus infinity are not calculated. The least value is x of minus 6. First I will write that x of minus 6, that is 62. Then comes x of minus 5, that is 30. After that you will get x of minus 4, 14. And after that you will get x of minus 3, that is 6. X of minus 2 is 2. X of minus 1 is not there, 0. And x of 0 is also not there, that is also 0. So just show where the origin is. So this is the solution for that. Okay. So moving on. Here, this you find the difference between the positive time sequence and negative time sequence. If it is negative time sequence, the power of z should be positive, and if it is positive time sequence, then the power of z should be negative. Okay. And here is a different problem. Given. So it says find the inverse z transform of. The problem is like this. Find the inverse z transform of x of z is equal to summation k is equal to 5 to 10 1 by k z to the power of minus k, where z is greater than 0. Now we have to find the inverse z transform. So before going to that, if you expand this, the value of k is from 5 to 10, so that will give you 1 by 5 z to the power of minus 5 plus 1 by 6 z to the power of minus 6 plus 1 by 7 z to the power of minus 7 plus 1 by 8 z to the power of minus 8 plus 1 by 9 z to the power of minus 9 plus 1 by 10 z to the power of minus 10. So now if you continue this, we have a z transform for delta n minus k. If you perform z transform, you will get z to the power of minus k here. Now based on that, if you observe, we have z to the power of minus 5, whatever the coefficient you have, so that will be, you can compare and you can iterate the coefficients here, but we have to find the inverse z transform here. So for x of z. So based on that, you can write it taking inverse z transform. So observe this, the quotient 1 by 5 remains as it is. Z to the power of minus 5 is the z transform of delta n minus 5. So that gives us x of z is equal to 1 by 5 delta n minus 5 plus 1 by 6 delta n minus 6 plus 1 by 7 delta n minus 7 plus 1 by 8 delta n minus 8 plus 1 by 9 delta n minus 9 plus 1 by 10 delta n minus 10. Or you can write this one, and since I have taken inverse Z transform, this will be x of n here. So x of n can be written as summation k varying from 5 to 10 1 by k delta n minus k. So you can express in this way, or you can just conclude this as the final answer. So both are right. So moving on, I'll take one more example before concluding this video. So given x of z is equal to cos 2z, where z is less than infinity. So now the expression for this, so the cos theta can be expressed in this way: 1 minus theta square by 2 factorial plus theta 4 by 4 factorial plus theta to the power of 6 divided by 6 factorial plus so on. So we can express cos theta in this form, that is the series expansion of this. Since we have z less than infinity, so x of n is present is positive time sequence because the ROC is less than infinity. Okay, so it is not selling. You might be considering why the negative sign is not considered, because if it is mentioned as infinity, means obviously it will be considered from 0 to infinity only. So therefore this cos theta can be expressed as summation k is equal to 0 to infinity minus 1 to the power of k theta to the power of 2k divided by 2k factorial. So what I have written here, this can be written in the short form in this way. So if you expand this, you will get the same thing from 0 to infinity. Okay, while giving the values for k, you will get this answer 1, 2, 3 and so on. So that is the simplest form of representing this cos theta. Now given x of z is equal to cos 2z. So that means in place of theta we have 2z here. So therefore we can express this as summation k is equal to 0 to infinity minus 1 to the power of k. Now in place of theta we have 2z here, 2z to the power of 2k divided by 2k factorial. Okay. Now if you go for simplification here, this 2 and z can be split into 2 here. So minus 1 to the power of k. So I'll take 2 here, 2 to the power of 2k into z to the power of 2k whole divided by 2k factorial. Now we have 1, minus 1 and 2, and 2 to the power of 2k, I can write it as 4. So let's write it down here. Minus 1 to the power of k, 4 to the power of k, z to the power of 2k divided by 2k factorial. Since we have minus 1, so that don't make any further changes. 4 and minus 1, both of them have a similar power, so we can combine them. So k is equal to, that is, we can multiply. So 4 into minus 1 is minus 4 to the power of k, and z to the power of 2k divided by 2k factorial. Now in the previous method, delta n minus k, if you take z transform, you will get z to the power of minus k. So you will get, if it is delta n plus k, so then it will be z to the power of k. So based on that, in place of k, we have 2k here. So that says we can write it as delta n plus 2k here. So taking, this is x of z. So we are taking inverse z transform for the whole term. Inverse z transform. So you can write x of n is equal to, the summation remains same, k is equal to 0 to infinity minus 4 to the power of k, and here in 2k factorial will also remain same. In place of z, we can write delta n plus 2k. So this is the inverse transform of del z power 2k. So that completes this one. Inverse transform using power series expansion as well as partial fraction expansion. If you have, I hope you have understood this power series expansion. If you have any queries, do comment or reply to this video. Thank you for your time.